In this video, I want to go over a couple of ideas about op amps that I can't find answers to after I've scoured the internet and looked through half a dozen engineering textbooks. And those questions I'll show you in just a second, but I'm going to answer something that basically a lot of people just kind of gloss over. They just say this is how it works, but they don't actually get into the details. And I was really curious about those concepts, and so I want to really dive into that in this video. And so with this, I want to start with the golden rules of op amps because a lot of stuff in this video will be based off of these two things. So what they tell you in class is that current doesn't enter the op amp terminals. And so if we think about an op amp, we know that internally there's a high amount of impedance. And so if we were to look at the internals of this, these two pins aren't connected together. And not only that, but they are there's a high impedance between them. So as a result, current doesn't go in because there's no place for it to go because it's acting like an open. And so rule number one is actually pretty easy to answer and to understand. It's rule two that kind of jumps into what this video is all about. And that is the voltage at each input terminal are equal to each other. And so that's one way to put it. And so sometimes they say there's such thing as a virtual ground. But the real important thing to understand about the second golden rule is this is only true if there is negative feedback. Okay, so what that means is if I were to ground one of these pins, then there's 0 volts there, and that means the other one should have 0 volts on it as well. And so again, that's only if there's going to be some sort of feedback. So we're going to look into that. But what is this video actually going to answer are these questions that you see right here. So what is a virtual ground? Why is it there and how does it work? All right, and so a lot of times people say, well, the rules are that there is a virtual ground there, and so you can work with that. But why is there a virtual ground there? And how does that interact with the output voltage? The second question I'm going to answer is, if both terminals have the same voltage, according to rule number 2, then why is there even an output at the output of the op amp? Because you know, an op amp is a differential amplifier, and so it amplifies the difference in the two voltages. And if the voltages are the same, why is there an output to begin with? And then the third one, and really the most important one that I really wanted to get to understanding, is how does the negative feedback mathematically equate to having the same voltage at each input? So, like I mentioned, there's a lot of videos in the textbooks that go into the output creates a voltage that gets fed back into the inverting terminal that opposes the inverting terminal and therefore causes that terminal to go towards 0, and then there's equilibrium. But they don't get into how that works mathematically, you know, with actual voltage values, and so it's something that I want to answer here. All right, so we're going to start with the easy one. We're going to start with the non-inverting amplifier. Okay, this one's actually pretty simple to understand, all these rules. So let's say we have a 1 volt input. We turn on the switch, and that means that the positive terminal will have 1 volt. Now, before we turned on the switch, there was no output voltage. It was 0 volts. So when we first start, there's no voltage on this inverting terminal. So the second we turn the switch on and the 1 volt gets applied, there's a difference in voltage. And that difference in voltage is the thing that's going to be amplified by the op amp. Now, if there was nothing connected here, then the amplifier, if this was a 741 for instance, has an internal gain of say 200,000. You know, some really high number, it might not be exactly that, but anyway, it's really high, so it's going to try to amplify the difference. And if the difference is 1 volt and we multiply that by a gain of say, we'll say 100,000, then the output would go up to 100,000 volts, which it can't ever do because it's actually limited to whatever rels we're set to. So let's say we operate this thing with plus and minus 12 volts. And so the output, if we had no feedback, the output would go up to 12 volts. And that's the big key of how feedback works, is it doesn't instantly go up to 12 volts. It gradually, quickly rises to 12 volts. Now, it's never going to get there if we have a feedback circuit like the one here. All right, so let's explain that part. And so if the output is going to go up because the positive terminal is higher than the negative terminal. If the positive terminal is higher, then the output goes higher. If the negative terminal is higher, the output would go lower. So right now the positive terminal is higher, so the output voltage is starting to rise. Now this one is easy to find online. You can find people describing this. It's really the non-inverting circuit in a second that is going to be more difficult to answer. So this one is just an easier example to start with so you understand the next one a little more easily. So as it starts to rise, eventually it's going to reach, it's going to try to go up to the 12 volts, but it's never going to get there. It's going to eventually get to, say, 1 volt. It's going to reach 1 volt. Now, obviously this is not drawn to scale. It's going to reach 1 volt on its way up to 12. But when it reaches 1 volt, because this is a voltage divider circuit, and these resistors, I sized them equally to make the math simple, the voltage right in the middle here would be half a volt. Now you look at that half a volt and you say, okay, is there a difference between these two terminals? And the answer is still yes. So that means the voltage is going to continue to rise. And at some point, the voltage is going to get to, say, 2 volts on its way up to 12 volts. Now it gets up to 2 volts. And this becomes a 2. And now this voltage right here becomes 1 volt. It's half of the output voltage because these resistors divide that voltage in half due to the voltage divider effect. And so now we have 1 volt and 1 volt. Is there a difference in voltage? No, there's not. And so the difference is 0, so therefore since the op amp is only going to amplify the difference and there is no difference, this 2 volts is going to start to go down. Right? Now it's not instantly going to go to 0 volts, and that's the key. If it instantly went to 0 volts, we'd be back to where we started, and we would just kind of be going up and down on this graph, and that wouldn't work. So the idea is it starts to go down. So let's say it goes down to 1.99, okay, on its way down. So that means this voltage is no longer 1. It's about 0.995, right? Starts to drop. Well, now that this dropped to 0.995, there's a difference between these two voltages again. It's very small. Now the delta V is 0.005, but the fact that there is a difference and you multiply that difference by the internal gain of this op amp means that the output is going to start going up again, back up towards 2 volts. And so now you can probably start to see where I'm going with this, is that if this difference causes the positive terminal to have high voltage again, then the output will start to go up. And once it reaches 2 volts, the output starts to go down, and basically it goes up and down and up and down, and kind of has an oscillation where it eventually settles in on exactly 2 volts. And so that's why the output voltage is 2 volts, and this is how the negative feedback causes these two terminals to be equal, yet there's an output voltage. And so that's one of the golden rules, was that these two voltages are equal to each other. And so what I want to really point out right here is these two voltages are not equal to each other if it wasn't for the output voltage. And so that's one of the things that people overlook when they talk about the golden rules, is that these these input voltages are equal when in fact they're only equal because there's an output voltage. Otherwise, they would not be equal to each other. So as funny as it makes it seem, the fact that there is an output voltage is what causes these two voltages to be equal to each other. And so it may seem like the output voltage should be 0 because they're equal, but without there being an output voltage, these two inputs wouldn't have a difference of 0 volts. Okay, so the output voltage actually causes them to be equal, not the other way around. And that's what's overlooked a lot in these videos, is it seems like the terminals cause the output to be had, but it's really the output that causes the terminals to be equal to each other. All right, so now that's one of the situations, and that's actually the easier one. The one that's really going to be quite more interesting is with the inverting op-amp configuration. Now, this might be something that you already know. I do want to run through how the output comes about in the first place before I go on to my explanation of how the output voltage causes the input voltage to be equal to each other. So eventually we're going to say that this is 0 volts and this is 0 volts. These two voltages are going to be equal. And so again, people say what the golden rule is. They say these are equal to each other, but why are they equal to each other, and how does the output cause that to happen? It's not the other way around. Okay, so before we go there, let's do just your basic understanding of how the gain of this circuit works, because that will come into play in just a second. So if you recall, no current enters these nodes or these input terminals, and so if the current coming in is 0, that means that there's basically kind of an open right here. And so I can actually just erase this line to show more visually that we have a circuit that kind of looks like this. Now, if we put, if we can assume, and I don't want to assume throughout the whole video, but for right now, in order to explain the gain, if we can assume that these two are equal to each other, then we can do the math to figure out the gain. But the problem is that's where a lot of books leave it, and it's like, well, why did that happen in the first place? I'll get to that. So if we have 1 volt right here, and we assume that these two are equal to each other due to the virtual ground effect, this is basically kind of like ground, virtually, it's basically ground, then that means we have 1 volt across this resistor. Okay, now notice I drew some polarities here because the left side is more positive than the right side. And so current will begin to flow, and I'm going to draw my conventional current direction, and that current would be 10 milliamps. And it's 10 milliamps just due to Ohm's law, 1 volt divided by 100 ohms. Now this current does not have any place to go except up through the feedback resistor. And that's because the feedback resistor is the only thing connected to the input resistor if this is acting like an open. So this 10 milliamps is going to go through, and we have 10 milliamps here. And so again, you're going to have 1 volt across this resistor because I sized these resistors to be equal. We can make these anything we want, and this could become any voltage we want. But in this case, I'm trying to keep it simple for the math that we're about to do. So there's 1 volt. Now you have to understand that the polarity of this resistor's voltage is the same as the polarity of this resistor's voltage because the current is still going in the same direction in both resistors. So we have to have a polarity that looks like this. And so if this polarity on the left side is your positive, and you attach the positive of your voltage polarity to ground, then the other side will be negative voltage. And in this case, it'll be negative 1 volts. Right? If you were to take a battery and you attach the positive value, the positive end of the battery to ground, then you're going to get negative voltage on the other side. You have no other option because this voltage has to be less than this voltage. This voltage, again, has to be less than this voltage. And if this voltage is 0, you have no other option but for this to be negative. So that's where we get negative voltage. And so you put in 1 volt, you get out negative 1 volt. Okay? Now that's assuming we have these two values at 0, which I still have to explain where that comes from. But before I do that, let me just go through the gain of this circuit, because this will come into effect too. The current that's right here, we're going to call the input current. And the current right here, we're going to call the feedback current, because that's the current in the feedback resistor. And those have to be equal to each other, because they are in series with each other. And according to Ohm's law, what I just said, the input current is equal to, in this case, 1 volt, or let's not do exact numbers, let's do general. The voltage input divided by the input resistor, and that's going to equal the voltage on the output right here divided by the feedback resistor. And this is a negative voltage because that's what I described before. And so if I rearrange these and I put this down here and put the feedback resistor up here, you end up getting V out over Vn, which is the definition of what gain is. How much more do you get out versus what you put in is going to equal the negative feedback resistor divided by the input resistor. Now, I say all this to say this is all true if we can assume these are both the same. But that's after steady state. That's after it's been on a while. And so what I want to answer in the remaining part of this video is, how does it get to that point, right? We understand there's negative feedback, and that's going to cause everything to kind of settle out this way, and that's the end result. But why? Why does it actually do this? And so that's really the goal of what I want to explain. So it's pretty simple, it turns out. Let's redraw this circuit. Okay, so if we look at the circuit, again, because of the high internal input impedance of the op amp, I'm going to pretend that these are just disconnected from each other. Okay, now when I first turn on this circuit, there's 0 volts at the output. And so what I want to look at is what happens during the transient response stage, where you just turn it on. How does this cause this to be 0? So I put in 1 volt, and because there's 2 resistors in series, the result is that this voltage here would actually be 0.5 volts. Okay? Now, because this is 0 volts, there's a difference between the 2 voltages, and so therefore the output is going to go from 0 volts, it's going to start going down, just like before. It's going to start going down because the inverting terminal is higher. So let's see what happens. Let's say it goes down and it starts going down to negative 0.2 volts. So if this is negative 0.2 volts, that negative 0.2 volts is right here. But we still have this same exact series circuit that you see right here. And so I'm going to draw negative 0.2 volts right there. So what is the voltage across this whole thing? It is 1.2 volts, right? The total voltage across here. So wouldn't this voltage now be halfway between these 2 voltages? And that's the trick to this whole thing. What is halfway between these 2 voltages? Well, you might say, oh, well, 0.6 volts. Well, it's not 0.6 volts, it's halfway between 1 volt and negative 0.2. And so we would be at 0.6 volts above this lower reference point, right? So halfway between 1, if you just did the average, right, 1 and negative 0.2, what's halfway between would be the average. It turns out that is now going to cause this voltage to go to 0.4 volts. Again, that's because 0.4 volts is halfway between 1 volt and negative 0.2 volts. Okay, well now this voltage went down. And so the difference between the inverting terminal and the non-inverting terminal, that change in voltage is actually starting to go down a little bit. Now this 0.4 volts is still going to cause, because there's a difference and because the inverting terminal is still higher, it's going to cause this to go down even more. Let's say it's now negative 0.4 volts. Okay, now instead of having 1.2 volts across the entire thing, we actually have 1.4 volts across the input to the output. And so right in between would be halfway. And what is halfway between 1 volt and negative 0.4 volts? Well, halfway between those, in the same idea, is 0.3 volts. Right? Because 0.3 is 0.7 volts less than 1 volt, and it's 0.7 volts higher than negative 0.4 volts, and so it's halfway between. And this is going to keep happening. So what is going to happen is, eventually, what do you think that voltage is going to go down to? Well, eventually, this will be negative 1 volt. And when this is negative 1 volt, from my input to my output, I have a total of 2 volts. And we know that this is still halfway between 1 volt and negative 1 volt, so this will eventually become 0 volts, since that's halfway between these two voltages. If this is 0 volts, now we've got 0 volts at my inverting terminal. And so you would say, we're done. Well, we're not done, because now we have no voltage across those points. And so this might start to climb, because it's gonna want to go back down to, it's gonna want to eventually go down to 0 volts. And so it's gonna go to, say, negative 0.9 volts on the way down to 0, because again, we would have 0 volts on the output if the two inputs had no difference between them. But as soon as this goes down to 0.9, then this causes this voltage to go up a little bit, back to maybe, say, 0.1 volts. And as soon as there's a 0.1 volt difference, that's going to cause the output voltage to not continue in that direction, but rather go back down towards the negative 1 volts that we just had a second ago. And so what's going to happen is, just like the other op amp, this will hone in through a series of oscillations to give us a 0 or a negative 1 volt output while maintaining a 0 volt input right here, because 0 volts is halfway between these two. Now this math will work out whether or not this gain is 1, like it is in this case, right? 100 divided by 100 is a gain of 1. Or if we add a 0 to this. If we add a 0 to this, now my gain is 10, right? 1000 divided by 100. And so if my gain is 10, the math will still work out. Let's see what happens. If I were to put in 1 volt with a gain of 10, eventually I'm going to make my output equal to negative 10 volts. And so the voltage at this point will be almost, again, acting like a voltage divider. So this voltage from here, we have 1 volt on the input and negative 10 volts on the output. Then the voltage here would not be halfway between these two values. It's going to be 1000 out of a total 1100 ohms, which is, 10/11ths of the difference of 1 volt to negative 10 volts, right? If I were to draw this vertically, if we're at 1 volt and we're at negative 10 volts here, and I draw my little resistors, and this resistor is 100 ohms, and this resistor is 1000 ohms, you can see that the voltage across this resistor here would be very, very high compared to the voltage across this resistor. And it turns out if you do the math with this voltage divider, then you would have 0 volts right there, right? Because this is going to take up 10 of those volts, and this one is going to take up 1 of those volts because this resistor is 10 times bigger than this one. And so again, whether I make this resistor 10 times bigger or 100 times bigger, you're still going to maintain the same 0 volts at this input. And so again, what's really important about all this is that even though it looks like these two voltages are equal, therefore you should have no output, it's the fact that there is an output that causes these two to be equal to each other. Okay? It's backwards from what you would think. You would think these two would cause there to be no output, but it's really the fact that there is an output that causes these two to be equal to each other. A little bit reverse. So that's basically how this works. I do want to show you a simulation to prove to you that what I'm explaining actually is real. So what you can see in this example here is instead of just putting a DC voltage source, I put a square wave in here to show how the effects are when you shut it off as well. But you can see as I simulate this green line right here is the square wave input voltage. And if you get lost throughout the remainder of this, you can look down here and see which color is which. So this green one is my input voltage, it's just a square wave. The blue one is my output voltage, and the red one is the voltage coming into this inverting terminal right here. And so you can see right here, the second I turn on my input voltage, because the output voltage is 0, the voltage right here in between should be halfway between 1 volt and 0 volts, which is half a volt. And that's exactly what happens. You see right here, that voltage gets stuck at half a volt. But only for an instant because that half a volt causes there to be a difference between these two inputs, the output starts to go down. And so this blue line you see starts to go down. And as you can see, as it goes down, eventually when it reaches -1 volts, and the output is -1, the inverting terminal, because these two resistors are sized the same, is halfway between the 1 volt and the -1 volt. Okay, and that's where it comes in. And what's really cool about this simulation is you can see, if we were to zoom in on this, you can see that it oscillates. So if we look in right here, we can see that this output voltage actually passes the set point it needs to eventually get to. And so when this happens, the output voltage goes beyond the -1 volts. Right here is going to be -1 volt. But if we make this output voltage -1.03 and it goes beyond its eventual settling point, that means it causes the inverting terminal to have a slightly lower voltage than ground, meaning we just went beyond the halfway point. You know, before the halfway point was 0 volts between 1 and -1, but now if we make the output -1.01, this inverting terminal becomes negative, which means the positive terminal has more voltage, right? 0 is higher than negative. And so if the positive terminal is higher, that's going to cause the output to start to go up. And that's exactly what's going on right here. It's starting to go up. But if the output terminal voltage goes past 0, where it would make this inverting terminal 0, then it would cause the inverting terminal to have a positive voltage with respect to the other terminal. And therefore the output would start to go down. And so what happens is it has this oscillation effect. It's going up and down, and eventually it settles in, but never fully. It actually just takes a long, long time, and so that's how these oscillators can begin oscillating towards a specific point. Now this is also true with that oscillation is also true with this red line, the inverting terminal. If we look at it, the inverting terminal is oscillating too, and that's because the output is oscillating. And so they're both oscillating, and therefore the inverting terminal causes the output voltage to change, which causes the inverting terminal to change. And so the big thing to understand is this inverting terminal voltage is basically halfway between the input voltage and the output voltage because these two resistors are equal to each other. And if these two resistors were not equal to each other, it still would work, like I mentioned before. If this was 1,000 ohms, or say 900 ohms, mathematically you would still get that same voltage effect where this voltage would be 9 times greater than the voltage across this resistor. And since the output is now 9 times greater than it was a minute ago, then the terminal here remains at 0. So to believe me further, I would like to show you at least one example from the ones I wrote earlier. So if you remember in the case where I put in 1 volt and the output was gradually going down negatively, at some point there was a voltage that the output would equal negative 0.2, and that means that the inverting terminal would have 0.4 volts across it. I want to show you that value in the simulator. So right here, if I were to zoom in on these voltages and I were to look at the point where the output voltage, or sorry, the input voltage at the inverting terminal was 0.4, right around here, and I use my cursor right here to hone in on that point, and I'm going to cause this to be equal to 400 millivolts. You can see right here when my Y value is 400 millivolts, my output voltage down here is negative 200 millivolts. And if I look back at my picture, that's exactly what was supposed to happen. At 400 millivolts on my inverting terminal, my output voltage was negative 200 millivolts, which is that value right there. So to recap, why is there a virtual ground? The virtual ground is there because there's negative feedback, and it's the negative feedback that causes there to be a virtual ground. It causes it, those two voltages to be equal to each other. So without negative feedback, all of this stuff falls apart. Why is there an output voltage if the terminals are equal to each other? Well, the terminals are equal to each other because there is an output voltage. It's actually, you should be asking the question the other way around. And then lastly, number 3, how does negative feedback mathematically equate to having the same voltage on each input? And that's what we did right here, showing that you're really looking at the voltage between the input voltage and the output voltage, and so the voltage right here will be somewhere in between, and therefore you can use the voltage divider rule to figure out what voltage there is in between, and it's always going to eventually settle on 0 volts.